Today's topic it is electric field due to uniformly charged spherical shell. It is another important 5 marks question from the chapter electric charges and fields. It is very important under the Gauss law, applications of Gauss law. So now consider a thin spherical shell of radius capillary and center O. Let Q be the plus Q be the charge on the spherical shell. So we'll take the one charged spherical shell here, positively charged one. This is one positively charged spherical shell. So we'll give the positive charge here. Of radius capillary. So O be the center and radius it is capillary. When point P lies outside the spherical shell, when the point P lies outside the spherical shell, we have to calculate electric field at a point P at a distance r from the center of the spherical sphere. At a distance smaller from the center of the spherical sphere. Now draw a Gaussian surface through a point P so as to enclose the charged spherical shell. Now we have to draw the one Gaussian spherical shell through the point P. This is the one Gaussian surface. Of radius smaller. The Gaussian surface is a spherical shell of radius smaller and the center O. Let E be the electric field at a point P due to the positively charged spherical shell. This is the direction of electric field due to positive charge E bar. Now consider a small area element around the point P. Consider a small area element around the point P. That area vector, it is always normal to the surface, so ds. So if we consider point P anywhere on the sphere Gaussian surface, the electric field vector and area vector both are parallel to each other. Then what is the flux through the Gaussian surface? Electric flux through the Gaussian surface. Area element ds. So d phi is equal to electric field vector dot area vector. So now what is the total flux through the Gaussian surface? total electric flux through the Gaussian surface. So we can write here flux phi is equal to integral E ds cos theta. So here theta becomes 0 degree because both are parallel to each other. Cos 0 it becomes 1. So then flux phi is equal to integral E ds. So here integral ds is nothing but 4 pi small r square, that is the area of the Gaussian surface. So if I substitute here E into 4 pi small r square, this is the equation number 1. According to Gauss law, the total flux, electric flux, is equal to 1 by epsilon naught times of charge enclosed by the closed surface. This is the equation number 2. From equation 1 and 2, LHS are equal. We can equate RHS. So that means E into 4 pi r square, that is equal to Q by epsilon naught. So then electric field E is equal to 1 by 4 pi epsilon naught Q by r square. This is the electric field due to charged spherical shell. The point P lies outside the sphere. Sometimes we can write here this, the charge reside over the spherical shell. Q is equal, that means surface charge density sigma is equal to Q by A. A means here area of the charged spherical shell. So that means 4 pi capital R square. So from here Q is equal to sigma into 4 pi capital R square. If I substitute this, so 1 by 4 pi epsilon naught into 4 pi capital R square into sigma by small r square. 4 pi will get cancelled. So then electric field E is equal to sigma by epsilon naught into capital R square by small r square. This is the another formula.